In this video, we are going to do a quick review over all our knowledge and skill about calculating probabilities, and we have a total of 18 problems to help us do that. Here's our first one. Suppose that 57 out of 110 students at a school are underclassmen, so freshmen or sophomores, and the rest are upperclassmen, juniors or seniors. Suppose 3 students are selected at random. A, what is the probability that all 3 of the students are underclassmen? Well, first of all, we're going to have to keep in mind that anytime you do probability is always the number of successes over the number of total possibilities. And so this is a piece that we are going to use on virtually every single problem in one way or another. So for this one, the key feature that we have to figure out is, well, how many total ways are there to pick 3 students? There's absolutely nothing that indicates that we need to be concerned with whether or not this is an important order, because the order in which they get picked is not relevant. That's what would let us know these are combinations. And so we would have 110 students, and we're choosing 3 of them. This piece here is the total number of ways that we could get everyone. Now, we're not going to take the time to go through and do the number crunching. You've got the calculators that'll do the formulas for you. Just plug them in quick, and you will get 215,820. We also need to determine the total number of successes that we would have. Now, a success is getting all 3 underclassmen. Well, there are 57 underclassmen to choose from, and we need to pick 3 of them. So how many ways are there to pick the 3 underclassmen? Well, once again, we'll crunch the numbers in our formula, and we would get 29,260. This, remember, was our number of successes. Therefore, we could calculate our probability, the number of successes over the total outcomes, and we would have our probability with this fraction. We're done. It is worth noting that you would want to simplify the fractions, though that's something I'll leave you to do. The second problem. What is the probability that all 3 students are upperclassmen? Well, this one's going to work out to be a little bit different. You'll notice we still have the total is the same, but the way we define success is now different. We no longer have 57 students to choose from because we're not choosing underclassmen. We would have 110 subtract 57, which yields 53. There are 53 upperclassmen to choose from, and when we use our calculators to crunch that, we wind up with 23,426 successes. And so we can put our success over total and get 23,426 over 215,820 for part B. And part B is done. This is our probability. Again, piece that would simplify, but we've got our answer. And I'm going to erase some of these other pieces to create room. Okay. Moving to part C, which I will do in green. What is the probability that there is at least 1 underclassman and at least 1 upperclassman? Well, you'll note this is a piece that looks 2 different ways. We would define success in this way if there was 1 underclassman and 2 upperclassmen, or we could have 2 underclassmen and one upperclassman. Either one of those ways would be considered a success. So what we are now tasked with doing is figuring out how many total ways are there that either one of those could happen. You'll remember this is like what we were doing in our 1.5. In order to do the first part here, which I'll do in purple, we have to remember there are 57 underclassmen, and we are choosing one of them. But then we have to multiply by the number of ways that there are to pick the two upperclassmen. There are 53 upperclassmen, and we would be choosing two of them. If we put this into our calculator to get the number of ways that we could have one underclassman and two upperclassmen picked at the exact same time, grab your calculator, start crunching the numbers, and you would obtain 78,546 ways to get one underclassman and two upperclassmen. Considering the other option, two underclassmen and one upper, that would say there are 57 underclassmen, we're taking two of them, 53 upperclassmen, we're picking one of them, and when we type those pieces into our calculator, we will obtain 84,588. So when you combine them, we have two different avenues to success. Our avenue in purple, where there is one underclassman, two upper, and the avenue to success in yellow, two underclassmen, one upper. When we add those two pieces together, we obtain 163,134. So our total number of successes coming back up to the top here. There are 163,134 successes out of 215,820 total possibilities. And we're done. I know I went through these pieces, especially part C, pretty quickly, but that's stuff that we were doing in 1.5. It's a review skill. Okay, part 2, or question 2. Two six-sided dice are rolled, one after another. Okay, so we have first one, then the second one. Well, please note that this is a piece that we could get by 1, 2, 3, 4, 5, 6 on the first. 1, 2, 3, 4, 5, 6. We could create the grid like we had done before. And for part A, we would like to know the probability that we get a total of 10 or more. Well, keep in mind that we would get 12 with 6 and 6. 6 plus 5 is 11. 6 plus 4 is 10. 5 plus 5 is 10. And then all the rest of these, we'd have our diagonal of 9, diagonal of 8, diagonal of 7, and so forth. But we would recognize our total number of possible outcomes. 6 times 6 are 36 outcomes. And we can count that there are 5 of them that have a total of 10 or more. Part A is done. Part B. What is the probability of getting doubles? Well, we still have 36 total outcomes. How many ways are there to get doubles? Double ones, double twos, double threes, double 4, double 5, double 6. There are 6 ways to get those doubles, so we'd have 6 out of 36. Okay, going to part C. Part C is asking us if the total is even or the total is less than 6. And listing out this total number of options would be beneficial. We'd have 9, 9, 9, 9, 8, 8, 8, 8, 8, 7, 7, 7, 7, 7, and I'm missing one more. 1, 2, 3, 4, 5, another 7, and 1, 2, 3, 4, and I'm missing a 6, 5, 2, 3, 4, 3, 3, 3, 2. Ah, dang it. Not having the lines has messed me up. Give me a second to put these lines in and actually help out, because not having the lines is just messing me up a bit. So we'd have, okay, taking our totals, 2, 3, 4, 5, 6, 7, 3, 4, 5, 6, 7, 8, 4, 5, 6, 7, 8, 9, 5, 6, 7, 8, 9, 10, 6, 7, 8, 9, 10, 11, 7, 8, 9, 10, 11, 12. Okay, there are all the totals. Now, how many of them are even or less than 6? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. I've just counted 18 of them that are even. But continuing further to get less than 6, 19, 20, 21, 22, 23, 24. So counting them all up, we can get 24 out of 36. So we can actually create the complete list and get that totally and completely valid method. You would also want to note another way of doing it. We could do this by saying the probability that it's even or less than 6. We had a formula that would say whenever you've got an or problem, you could look at it as saying it's the probability of the first. Okay, I wrote total. I wanted to say even. The total is even. Plus the probability that we get something for the second. But then we have to subtract off the probability that it gets both. And we saw that this was a formula that was true based on Venn diagrams. We're just showing a second way to be able to do this problem. Well, what's the probability that it's even? How many ways are there to get even? That's half of them. We knew that there were 18 out of 36. How many numbers were less than 6? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There were 10 of them that were less than 6. But when we consider the ones that were both, and I'm going to switch this one to red so we can see it a little bit better. So we need even numbers that were less than 6. That's 1, 2, 3, 4. We'd subtract off 4 out of 36. So 18 plus 10 is 28. 28 minus 4 is 24. And we have an alternate way that we can do it. We actually have our choice of which ones that we need. Okay. In order to create some room on this, running out of some space. I didn't want to do that. I'm going to take a moment and erase some of my grid. All right, continuing further now, we'll look at question D. Question D is asking, what is the probability that we get an odd product? Okay, remember odds are numbers like 1, 3, 5, 7, 9, and product is multiplication. So if we want to know the probability that we're getting an odd product, we would have to understand that the only way to get an odd product is to take an odd number times an odd number. Well, if we're looking at an odd number times an odd number, we could go through and completely fill out a new grid, 6 by 6, that's perfectly fine. Or we could just go through and say, here's an odd times an odd, 1 times 3, 1 times 5. None of the 2's would work, but 3 times 1, 3 times 3, 3 times 5. None of the 4's. 5 times 1, 5 times 3, 5 times 5. If we understand that we have to have odd times odd to get an odd product, we can just look at it that way and count. Not even knowing what the numbers are, we can see that there are 9 stars. Those are all my successes out of the 36 possibilities. And so that one's finished up as well. Okay, continuing with part E. The probability that the first number is greater than the second. Okay, so if this one's our first and this one's the second, let's just do a quick count. We don't even need to know what the numbers are. We just got to do a quick one and say, well, what do we have? 1 is not bigger than 1. 1 is not bigger than 2, not bigger than 3. So none of the first row would work. 2 is bigger than 1. It's not bigger than 2 or any of the others. 3 is bigger than 1. 3 is bigger than 2, but not the others. 4 is bigger than 1, 2, and 3, but not the others. 5 is bigger than 1, 2, 3, 4, but not the others. 6 is bigger than 1, 2, 3, 4, 5, but not itself. Each one of the stars were a number that where the first is bigger than the second, so count them up. How many total are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. We would get our answer that it is 15 out of 36. Simplify it, we're done. For part F, the probability that a 6 or a 3 is showing on at least one of the die. Okay, so when we're looking down here, let's consider where are all the different ways that we could get a 6 or a 3. Well, we would get this 3. It works on all of those. And for a 6, we could say we'd get all of these ones. Those are the options for the first die, but we could also have a 3 on the second one. So I'm filling in the column now. Or we could have a 6 on the second one, filling in this column. And then we've just got to count up how many total stars are there. 6, 12, plus 4, plus 4. We wind up with a total of 20 out of 36. And so we could create the sample space using a grid, and this is one correct way to do it. But again, please keep in mind, this is an OR problem, so if we wanted to do it differently, we could say the probability that we get a 6 on the first, or rather a 6 or 3, let me rewrite this. For the first die, we could say probability of getting a 6 or 3, plus the probability of getting a 6 or 3 on the second, but then the probability that they match on it. Well, this row is our first one. How many stars were on that? There were 12 out of 36. The second probability is our column. A column of 3 or a column of 6. That's another 12 out of 36. But how many stars are showing up on both? You've got it here, 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 and here. Those 4 are showing up on both of them, so we'd have to subtract off our extra 4 that got doubled up on accident. And so we'd have 12 plus 12 is 24. 24 subtract 4 does give us our 20. And so we've got the same answer, 20 over 36. Whether doing it with creating a list of options or if we were doing it by using the formula. Okay. So for the last one, part G, this one is asking us what is the probability that we have an odd total or a 2. Okay, well, let's start saying where's the odd totals. Remember, an odd total is a sum. So we would have 2, 3, 4, 5, 6, 7, 8. I went too far on that. It only goes up to 7. Oh man. Let me get rid of this 8. Didn't want that. There. And then we'd have 3, 4, 5, 6, 7, 8. 4, 5, 6, 7, 8, 9. 5, 6, 7, 8, 9, 10. 6, 7, 8, 9, 10, 11. 7, 8, 9, 10, 11, 12. And I'm just quickly replicating the total part again. So where do we have an odd total? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 of them that are odd, or a 2 is showing. Well, a 2 is showing means we got a 2 on one of the dice, so it's this whole row. So we had 18, 19, 20, 21, or this column, 22, 23. Counting it up, we can see that we have 23 out of 36 that would work. We can create the list and just count up how many successes we have. Keep in mind that if we wanted to, we could also go further and just back this piece up and do it with the formula. Question 3. A pet store owner surveys his customers during the day, and he finds that 15 own dogs, 9 own cats, and included there were 4 customers that owned both. Part A, draw a Venn diagram. Okay, so Venn diagram is going to overlap. We have dogs, we have cats. Okay, remember, in the dogs section, the entire circle needs to have 15. In the cat circle, the entire circle has to have 9. But we were also told that there were both. Well, when you look at the total dog circle, that's not 15 anymore. We've gone too far. The whole circle has to add up to 15, and for this particular part, we're going to have to back this part off. 15 subtract the 4 is 11. And we likewise encounter the same problem with cats. Cats has to be a total circle of 9, but we've got 13. Well, we will have to subtract off the doubled up portion to get just 5, and there we go, we're done. For part B, how many total customers were surveyed? Well, just add up the numbers. 11 plus 4 plus 5 gives us a grand total of 20. Add up each of the numbers in your Venn diagram, you get the total amount. Now we will look at it and say, what is the probability that they own a dog? Well, remember, successes over total. In the dog circle, we have 15 successes, but we just calculated there were 20 possible people. For part D, what is the probability that they own a dog? Then you should see the vertical line, the probability that they own a dog, given that they own a cat. This is the first one that we've been looking at that say given. Whenever we say given, it's going to change the total amount that's possible. We are saying probability that they own a dog, given that the only people we are considering at all are cat owners. Well, when we're looking at this piece, then, these are the only people for this problem that exist. Given that they own a cat, how many are there? That's 9 people who own a cat. So because of this part, that's what tells us our denominator is going to be 9. How many people own dogs from that group of 9? 4 of them. And part D is done. For part E, this one is asking what is the probability that they own a cat given that they own a dog. Exact backwards then. This is the group that says if we're only considering people who already have a dog, this is the only group we're allowed to examine. Well, if that's all that exists for us, there are 15 people in that yellow circle. How many of them also own a cat? That was 4. And this one's finished. Problem number 4. Suppose that 40% of all adults in a certain town are females, 60% are males. In addition, 60% of the females have full-time jobs, 80% of the males hold full-time jobs. Draw and label a tree diagram that represents this situation. Okay, so for part A, what's the first option that exists? Oh, didn't mean that to happen. Need this to be here. We could have male or female. The next part that we would look at is, do they have a job or not? And I'm actually going to switch this up so that instead of J or N, I'm going to have Y or N. Do they have a job? Yes or no. For women, do they have a job? Yes or no. Well, here's our tree diagram. What we need to do then is write down all the probabilities. The first piece that we have is, what is the probability that they are a man? Well, there is a 60% chance that they're a man. What is the probability that they're a woman? We were told 40%. For men, what is the probability that a man has a job? We were told that's 80%. What is the probability that a man does not have a job? Well, we know probability's got to add up to 100. So if we have 80%, what's the amount that gets you up to 100? 20%. When we're looking at females, what is the probability that a woman has a job? Well, we were told this one is 60%. So if 60% have a job, what percent don't? That's 40%. This whole part, this whole tree diagram, that's part A. Part B. What is the chance that a randomly selected person holds a full-time job? Well, that's an instance that we're looking at yes and yes. We have 2 different paths to success. A man can have a full-time job, or a woman can have a full-time job. If we would like to get the probability for those pieces, we could look at it and say, if we want the probability that a man has a full-time job, we just have to multiply the numbers, multiply the probabilities on this path. That's 60% times 80%. But we've got to add in the other option, a man or a woman, 40% and 60%, so 0.4 and 0.6. So when we have these numbers, we've got our answer. So just crunching them, 0.8 times 0.6, that's 0.48. 0.4 times 0.6 is 0.24. And when we add those up, 0.48 plus 0.24, that's 0.72, which of course tells us 72%. In this particular town, 72% of people have a full-time job, which we know is, generally speaking, pretty unrealistic. Even with unemployment as bad as it is, 72% is still pretty low. We'll also note though that does say full-time job. It does not say part-time job or anything else like that, or possibly having 3 part-time jobs. And because I'm weird, Halloween at my house, kids spin a spinner, has 3 equally marked spaces that are labeled 1, 2, and 3. So we'll have this part, and I'll try to do something that's bad. So here, 1, 2, 3. And I know they're not actually equally spaced, but we'll go with it. The number they spin depends on the number of pieces of candy in my bag. I start off with 20 chocolate bars, 30 sugar bombs, identical packaging. Trick-or-treaters pick randomly out of my bag after they spin, and I only restock my candy bag after each child finishes picking all their candy. Okay, so I restock after the kid picks, which means as they're picking, once you pick the first candy, you can't pick it again. This is an indicator that we're picking without replacement. So for part A, understanding that this is without replacement, we would have to say, what is the chance that they get to pick 3 pieces of candy? Well, the spinner tells them how many pieces of candy they get to pick. The probability that they get a 3 for 3 pieces of candy, 1 out of 3. For part B, suppose that they actually do spin a 3. So if they've spun a 3, then that means you get candy number 1, candy number 2, candy number 3. What is the probability that they get 3 sugar bombs? Okay, well, for 1 sugar bomb, how many successes are there? You're starting off with 30. Out of how many total candies? 30 plus 20 is 50, so for the first one, there was 30 out of 50. If you assume that they've picked a sugar bomb for the second one, then that's telling us it's 29 successes out of 49 remaining candies. And if they pick another one, that would say that there are 28 out of 48 remaining sugar bombs. And so when we crunch those numbers, we can just say 30 times 29 times 28. That would give us 24,360. And for the denominator, 50 times 49 times 48, that's 117,600. And there we go. We have our probability. It definitely needs to be simplified, but we've got our answer. Moving on to part C. Suppose a trick-or-treater spins a 3. Okay, so they spin a 3, so it's candy 1, candy 2, candy 3. What is the chance that they pick 3 chocolate bars? Okay, so once again, we've got 50, followed by 49, followed by 48. This sequence of 50, 49, and 48 comes from the fact that it's without replacement. Well, if we're going with 3 chocolate bars, originally you have chocolate bar, 1 less, 1 less. So taking 20 times 19 times 18, we get our total number of successes, 6,840, and our denominator would still be the same. And we've got our answer. Moving on to part D. What is the chance that the trick-or-treater gets only 1 chocolate bar and nothing else? Okay, so if we're saying and nothing else, that's saying, first of all, they have to spin a 1 on the spinner. After getting a 1 on the spinner, then, equivalently, this then is an and. So they get a 1, and then they get a chocolate. Well, we're looking at two different things. What is the probability that they get a 1, followed by the probability that they get chocolate? Well, the probability that they get a 1 was 1 out of 3 on the spinner. The probability that they pick chocolate was 20 out of 50 pieces of candy. So when you multiply those, 1 times 20, 3 times 50, and we get our probability, although that probability does still need to be simplified. And then lastly, what is the probability that they get exactly 1 chocolate bar and 1 sugar bomb? Okay, so this is done a couple different ways. This could be done as a probability that they get a 2, then they get a chocolate, then they get a sugar bomb. Well, for this particular piece then, we're noting our probability done this way has 3 stages. What they get on the spinner, what they get for the first candy, and what they get on the second candy. So probability that they get a 2, 1 out of 3. Probability that they get chocolate, there are 20 chocolates out of the 50 candies. Probability of getting a sugar bomb, there are 30 sugar bombs, but after getting chocolate, there are only 49 candies left. So multiplying these pieces, 1 times 20 times 30, that is equal to 600. And 3 times 50 times 49 gives us a denominator, 7,350. So this part gives us the probability of getting a 2, then a chocolate, then a sugar bomb. But we discounted the possibility that you can get the 2 and get the sugar bomb first, then get the chocolate. These are 2 different paths, and so there are 2 different probabilities. Well, probability of getting a 2 multiplied by the probability of getting a sugar bomb, 30 out of 50, multiplied by the probability of getting chocolate. When you multiply all those things out, you get, once again, 600 out of 7,350. Because these are 2 different paths, we have to add them up, which gives us the total probability, 1,200 over 7,350, which again needs to be simplified, but we've got our answer. Question 6. Suppose the table gives the breakdown of the ages and genders of teachers at your school. Find the probability that a randomly selected teacher is... Well, before we do a bunch of these things, anytime you have a 2-way table, first thing you want to do, get your row totals, get your column totals, because that's what we're going to use for everything. 5 plus 12, 5 plus 7, 6 plus 7, 18 plus 13, 7 plus 4, 5 plus 11 plus 18 plus 7, 25 plus 11 would be 36, 7 plus 7 plus 13 plus 14, that's 31, and when we add them up, we get the grand total, 67. So this is telling us that there are 67 total teachers in the school. Why did we go through and do all that stuff? Well, we needed it so that we could get the total. For part A, the probability that we have a male teacher, well, how many total male teachers are there? Add up the row, and you get the total number of successes for men. Out of how many total teachers? 67. And part A is done. Part B, how many are 39 or younger? Well, 39 or younger are this group, which if we added them up is that group. 12 plus 13 tells us that we have 25 successes out of the total of 67. part C, what is the probability that they are male or at least 60? Well, we can do this a couple different ways. Male, 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 male. And then I said 60, at least 50. We can take all the men, which was the 36 again, but then add in the women who are over 50, which is 4. 36 plus 4 would tell us, just adding up each of these numbers, that would be 40 out of 67. One correct way that we can do it. Again, we could still use our formula. The probability that they are male, 36 over 67, plus the probability that they're at least 50, which was there, but then we'd have to subtract the probability that they are both. Both comes from the 7. So 7 over 67. If we took 36 plus 11, that gives us 47. 47 subtract 7 is 40. And there we go. We can do it based on adding up the correct pieces in our table, or we could use the formula. Either method is correct. For part D, from 30 to 39, find the probability that a teacher is between the ages of 30 and 39, given that they are a female. So we're saying the only group that we're interested in are women, which tells us all this stuff for men. Given that we are saying female, that group does not exist. Well, if that's the case, how many total are there? Total of 31 women. How many are in the 30 to 39 range? 7. So our probability then is 7 successes out of the 31 possible women, given that they're female. Lastly, for part E, find the probability that they are female, given that they are at least 40. So if a person is at least 40, it says these ages don't exist in this problem. How many total people are there? 31 plus 11 would give us a total of 42 people. So there are only 42 people who are being considered because there are only 42 in this group of 40 or more. So what's the probability that they are a female? Well, the females are this group. 13 plus 4 is 17. And we're done. Question 7, here's another two-way table. And what do you always do right away at the start of a two-way table? Get the row and column totals. We're always going to use them. So 14 plus 8 plus 2, that's 24. 11 plus 9 plus 3 is 23. 12, 5, 5 is 22. 7, 6, 13 add up to be 16. Adding our rows, 14, 11, 12, so 25, 37, that's 44. 8, 9, 5, 6, 17 plus 5 is 22, that's 28. 2, 3, 5, 3, that's 13. And when we add them all up, we get our grand total. 5, carry over that 1, 4, 6, 7, there. So, what is the probability that somebody has a Ford? 23 Fords out of a grand total of 85 vehicles. We're done. What is the probability that they have a truck? Well, trucks, you'll come over on the row, 28 trucks out of a total of 85. What is the probability that they are a van or a Toyota? Well, van, 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 Toyota, Toyota. We could add up all of those numbers. And if we added them all up, we would get our successes. Or we could take van plus Toyota minus both. So how many vans are there? 13. How many Toyotas are there? 16. How many are both? 3. Well, just crunch your numbers. 13 plus 16 minus 3. That would give us 26 successes out of a total of 85. And question C is done. Question D, what's the probability that it's a car given that it's built by GM? Okay, so given that it's built by GM says this is the only thing that we care about. Ford, Chrysler, Toyota don't exist for us. Well, there are a total of 24 GM cars, or GM vehicles. And how many were cars? 14. For part E, what is the probability that it's a Ford given that it's a truck? Well, given that it's a truck says this is the only thing that we care about. So how many total are there that are trucks? And how many of those are Fords? We're done. Question 8. 2 cards are dealt from a standard deck of 52 without replacement. Big clue there, without replacement. So we have card 1, card 2. Well, what is the probability that both cards are face cards? Remember, face cards are the king, queen, and jack. So there are 3 face cards per suit. Since there are 4 suits, we'd have 3 times 4 gives us 12 face cards. Well, that means there are 12 face cards out of the 52 for the first one. Assuming that we got a face card on the first one, that means there are 11 successes left out of the remaining 51. And so multiplying that out, 12 times 11 equals 132. And 52 times 51 equals 2,652. And problem 8 is done. Question 9. A baseball player has a batting average of 250, which means he averages 1 hit for every 4 times he comes to the plate. What is the probability that this player will end up with exactly 2 hits if he comes to plate 3 times in a single game? Well, there are lots and lots of different ways that we can do this one. I personally think the best strategy for my brain is to do a tree diagram. Here's at-bat number 1. He could get a hit, or he could get not. For at-bat number 2, he could get a hit, or not, hit, or not. And then we've got at-bat number 3, hit or no, hit or no, hit or no, hit or no. We could create a tree diagram this way. And we know every time he comes up, he's got a 25% chance, 1 out of 4. And so what we're looking at is saying, how many ways are there to get exactly 2 hits? Well, you've got hit, hit. I want to switch colors on this. Hit, hit. Well, that's 2 hits, so he cannot get a third. So that's 1 way. He could have hit. I'd like to back this part up and simply, well, I should leave it alone. I'm going to switch colors here. Then he could have a hit, not a hit. Well, he'd have to have a second hit then. Or you also have the possibility that he could have no hit, get a hit, get a hit. These are the only 3 ways, the only 3 paths that lead to getting exactly 2 hits. Well, we can start filling in the numbers, remember, with the probabilities. Chance of him getting a hit is 1 out of 4. So the chance that he fails is 3 out of 4. Getting a hit is 1 out of 4. Chance that he fails is 3 out of 4. That he fails is 3 out of 4. Getting a hit is 1 out of 4. Getting a hit is 1 out of 4. Chance that he gets a hit is 1 out of 4. So if we would like to get the probabilities, we can say the probability of our first path, 1 out of 4 times 1 out of 4 times 3 out of 4. This is our probability for the first path. When we take the probability of the second path, 1 out of 4, 3 out of 4, 1 out of 4, which gives us 3 out of 64. And the probability for the third path, you'll note I'm just writing down the probabilities for each step along the way, gives us 3 out of 64. These three pieces are the probabilities for each of the individual paths that we had. So the probability of all three of those combined, 3 plus 3 plus 3, gives us 9 out of 64. And we're done. Given that the video is getting a little bit long, we'll stop here and we'll create another video that will continue with problems 10 through 18.